Hello, here we are again for Advent of Code, day number 10. I wasn't really planning to do it just directly the day after, but the puzzle of today is again very interesting, and it allows me to show a kind of pattern that is possible in 42 that is quite unusual and doesn't seem to be easy enough to be practical in other languages. So the idea is that we want to have a parser where we just have to parse balanced parentheses. And we have four kinds of balanced parentheses. In the first part, we have to check which lines have an actual syntax error. That is, they have a parenthesis inside that is not the right parenthesis that should go there in order to close the last open parenthesis. For part 2, we have to complete the string. That is, we have a string that doesn't close all the parentheses, and we need to discover which are the missing parentheses. I'm sure there was some direct solution that was like hard coding the specific kind of parentheses and make a solution that just works for those four kind of parentheses. But I wanted to try to be more general and make a solution that could be easily extensible if you have more kinds of parentheses. I'm defining an interface for any kind of parentheses. And this interface will have an open class method that gives you the string that represents the open parenthesis for this kind of parentheses. The close method that gives you a string that represents the string for the close parenthesis for this kind. And then, since this puzzle wants to give points for parentheses and the points depend on the phase, we have those two methods that are just here for the sake of the puzzle. We check if a certain string match this parenthesis in opening or in closing. The idea is that we want to make a linked list of those kind of parentheses so that it's easy to enter in a new scope or check if the last scope is the right one that we are trying to exit from. And it also means that it's going to be very easy to see which are all the open scopes, and that's going to be useful for part 2. To the same, we make a next method that return this dollar interface that represent our kind of parentheses. To model our data structure as a linked list, we also need the method push that will take a string and push the right kind of parenthesis on top of the current parenthesis linked list. And if the string is a closed parenthesis and we can close that parenthesis, the push will actually basically be a pop and remove the extra parenthesis. We also have an exception, as you can see here. And the idea is that if we try to close a parenthesis that is not the last open one, we will just throw as an exception the parenthesis type that represents this new parenthesis we could not close. Finally, we want to be able to create instances of dollar without knowing exactly what is the type of dollar. And so we have a method that just takes another kind of parenthesis and wrap it around, doing, if you want, a more literal push operation. We then define all kinds of parentheses that we are aware of right now. So the round parenthesis, the square parenthesis, the curly parenthesis, and the angle parenthesis. We then make a list of those parentheses type. And since in 42 I still don't have a list type for class types, we have to make a par B wrapper that contains our class $par. Then we have our cached parse method that just returns the list with all the type of parentheses that we are aware of. Then, as we have seen for another of the exercises in the Advent of Code, I make a trait to help me create many classes that are very similar but just have some holes. In particular, the current trait implements fits open and fits close by just checking if the provided string is equal to the open or the close of this class. And the open and the close are the handler method for the template pattern that we are making. That is, fits-O and fits-C are template methods whose behavior depends on the handler methods open and close. We then implement the generic factory by propagating the standard factory. The method push is possibly the most interesting part here. As you can see, there are 4 lines. In the first one, we check if the current character that we have to process is good to close our current parenthesis. And if that's the case, we just return the next element in our linked list. That is, we pop one element. Then, for all the elements in our list of parentheses, we check if the opening of this current element fits the character that we have at hand. And if that's the case, we just return this kind of parenthesis. Notice how we don't know statically which is the dynamic type of the object that we are creating. Then in line 3, if none of line 1 or 2 succeeded, we start to go in the error situations. So if the parenthesis that we are reading now fits the closing of one of the elements in the list of all possible parentheses, we just throw that element as an exception. In this way, this exception basically means I encountered this unexpected parenthesis after parsing this tail. Finally, in line number 4, if we have a character that is not predicted by any of our parentheses in one way or another, we just throw a custom error. At this point, you may be wondering why I'm using a lot of classes with the $name. The idea is that we're using the organized decorator. The organized decorator allows us to use a more friendly ordering of introducing concepts when we write our class, and then automatically rename those convenience names that have the dollar inside into more appealing names for the user of our code. That is, in this case, the user of par. Dollar is going to be renamed into top level, that is par. Round dollar, square dollar, curly dollar, and angle dollar are going to be renamed in round, square, curly, and angle. Here, we actually define the rest of round, square, curly, and angle. So the idea is that in this way we can define the class in 2 parts. We first define what we strictly needed in order to make our trait. Then, using our trait, we define all the other parts of round, square, curly, and angle. In particular, since we are following the template method pattern, we have to define the behavior for the 4 handler methods. That is, open, close, the points for part 1 of this puzzle and the points for part 2 of this puzzle. Since we have a linked list of parentheses and we don't have null in 42, we have to define a way to terminate this linked list. And so we can define a special AND kind of parenthesis that will have an open and a close with different symbol that doesn't appear in our string at all, and then we can have points to 0, for example. Finally, we still need to define the standard factory method, and in this case we will just trash the next parameter because AND have no fields. Indeed, the next method of AND just returns this. As you can see, next don't need to be a field. Next can be a field if we don't implement it. If we don't implement next, data in, for example, angle and curly here is recognizing that next is still an abstract method and is lifting it up to be a field. But in the case of AND, we provided implementation for next, and so in AND, we have no fields. After all the effort of defining our par class, the main is now very simple. The main that you see here actually represent both part 1 and part 2 in like 10 lines or something like that. So we have a local variable to accumulate the points for part 1, a local variable PS to accumulate the individual points for part 2. And then for all the line in our file, we have a variable points2 initialized with 0 because we have to do an inner accumulation level. And we have our parentheses to start with AND. Again, since AND have no fields, we can just initialize with open close. Moreover, in 42, any object that have no fields is implemented as a singleton. Thus, we can make as many par.end as we want without encumbering the memory. Thus, terminating our linked list with the par end, or if 32 were to support in an actual null, it will actually have the same exact performance. Then, for all the characters in our current line, we just do a par.push of C, and we assign the result to par. As you can see, our linked list is basically immutable, and so the push is creating a new linked list that looks like the old one but is pushed. One of those push may fail, and so we insert a catch. And the catch will capture a par, because that's the kind of exception that we are throwing from the push. And the exception signals that we have parsed a wrong character, a character that just should not be there. And so this is what we need to do for part 1. We have to capture which kind of parenthesis was out of place. We have to extract the points of that parenthesis and accumulate all of that to points 1. And as you can see, once you properly embrace dynamic dispatch and you make your code properly object-oriented so that so much of the behavior is covered by dynamic dispatch on some object in your domain, stuff like this become exceptionally easy. If there is no exception while we parse the line, we will reach line 76, where we just use an old school while to iterate over our linked list until we reach the end, and we recognize the end by checking the points equal 0. For each iteration in the while, we just take the points of the current head and we accumulate it in the way the puzzle wants to the current result, and then we go next in our linked list. After the while, we will have accumulated our result in points 2, and we can just add it to PS for further reuse at the end of the puzzle. To get the results, in part 1 we just print points 1, while for part 2 we will sort the list of points, and then we will call val to take the element in the middle. I really need to add to Adam Towel some useful max, min and sorting features, but for now, look, my cool one-line implementation of a sort. It's a little bit fun, it's very slow, but it's doing the job. It's extra duper short. See you next time for more 42. Bye! High five!